Alright, I'm back working on this tiny little operating system, and what are we doing? Yesterday, was it yesterday? Last time I was working on this was working on implementing dynamic memory allocation. So I needed a malloc, so I made a super shitty one. Maybe I'll just talk about how that goes. Refresh my memory before I start working. Alright, so basically this malloc needs to, well, I mean, store. Okay, so when on like user space side, malloc needs to ask for memory from the operating system, right, and then handle that in some way, because the operating system is going to give it back. So the kernel gives you back pages. So I made a system call just called get pages that you give however much you want, and oh, what's up, Sam Sepio? What's up, dude? Um, yeah, so you just get back how many pages, and then malloc needs to handle that. So the way I'm storing, um, the metadata, like what's the size of the blocks you're storing and stuff, is in this thing called an implicit, you know, free list. So, where's that book? This book's where I learned it from. Computer Systems Programmer's Perspective. It's a great book. Read it. So it looks like this, right? You have a header, which is stored before each block, which is a 32-bit word, 32-bit integer that stores the block size and whether it's allocated or not. And this little operating system is for like a 32-bit RISC-V CPU, so the um, blocks are always going to be aligned to 4 bytes, 4-byte boundaries. So what that means is that the low 2 bits are always 0. That's why you have these free to store, whatever you want. We're only using one to store whether it's allocated or not. So you have the header, and then the payload, which is whatever data that's going to go in there, and then optional padding to keep it 4-byte aligned. Um, yeah, and so you have this 2 special blocks that are stored in the heap. There's a prologue and an epilogue. So the prologue just gives you like where it starts, and the epilogue uh, is a 0, so it has size 0, but is marked as allocated. And so if you ever are traversing through this list and you hit a 0 size block that's allocated, then you're at the end. Um, so, you store like a pointer basically to the beginning of the heap, and you just start traversing. You look at the first one, tells you its size and whether it's allocated. If it's not, then you jump size ahead to the next one. And if that's free and you have enough size there, you can drop a block there. Right now I'm not doing any coalescing at all, so yeah, it's a super shitty malloc, but we're trying to get started. The whole, like, I wanted to work on a shell, like a little shell. I have had a super, super shitty one, and I'm trying to make a slightly less shitty one, and it'd be super useful to have dynamic memory for that, so I'm implementing a malloc. What I really want is a realloc so I can make, dynamic arrays. So I'm going to try to do that today. If I can get realloc up, then maybe start trying to, parse command lines into like arguments and make some little built-ins for a shell. Let's see, I should type over here so you can see. So let's swap these. Yeah, so I mean I can walk through how like the code works. So malloc init happens lazily. So the first time anyone calls malloc, well, the first time a process per process, so the first time a process calls malloc, it will initialize, which just sets up those epilogue and prologue, right? You'll jump in here. Depending on how much you ask for, it'll just line it up to a page size, and then make the system call get pages to get new memory from the kernel. Kernel gives back pages, and then you set up the prologue, the epilogue, and the first block you just mark, that many pages is empty, and that's it. So then where was I in malloc? Yeah. So after you init, you try to find an empty block. This is that like traversal of the heap I was talking about, where you just go from header to header trying to find an empty block. If you can't find one, well, then we ask the kernel for more pages. But if you can find one, you just place it there, which basically if the block is bigger than what you're asking for, then it'll chop it into two. It'll make one of the size you asked for, and the second half of that is now going to be not allocated. Then you write the header there, and you need to move the epilogue each time too. Yeah, so place does that, and then if you can't find a spot and you have to get more from memory from the operating system, then you move the epilogue there too. So let's try to make realloc now. So I think it goes, yeah, right here. Alright, let's do it. So any of the allocation functions, so malloc, realloc, and calloc are going to have to initialize malloc. So, if you haven't initialized, do that. Then what are we going to need to do? So realloc takes a pointer and a new size, and so there's a few cases you can have. You either, well, first of all, new size can either grow or shrink it, so we got to think about that. And then you just got to find a block that the new allocation can fit in, and then move everything over. Just copy the memory over. So let's do that. So let's see. So first we just need to check the header and see what the old size was, I guess. Like current size, we'll call it old size. What do I call it? Block get size. So I just have these like macros that given a block pointer, like a pointer to the payload of a block, will step back, 32 bits and read the header. And then, have some bit masks to get the size and the allocated bit. So old size is this. You say if new size is greater than old. Well, let's see. Which one did we do first? I guess we'll do bigger. So if new size is greater than old size, this is the common case. Welp. Let's search for ASMT, hold on. Alright, so if new size is greater than old size, we got to find a new block. So we just find fit. We get like a new block pointer. What do we call it? Malloc find fit. Which takes pointer in the new size. I mean, we need to wrap up this. This is the exact same thing we do here, right? It's just this and this. So, what do we call that? That's like... It's like find a fit and grow if you need to. We could just call that like... Well, am I being dumb? That's just all of malloc, right? So what we should do is just like, if new size is greater than that, well, we can just call malloc on it. And then copy over. This is all the rest we have to do, if I'm not completely... malloc new size. And then... essentially... do I have memcopy? Oh shit. Oh, it's in common. Okay, I did make a little memcopy. Okay. So I don't have libc because we're on you know, our known operating system. Okay. Alright, so copy from there to there. I always forget, what was it? Was it dest first, I think, right? Memcopy into here from here. Let me make sure. Dest source count, yeah, old size. Okay. What is this? Return. Like, it doesn't really matter, does it? Alright. We also have to handle... well, we're gonna need that. We'll start at here, right? Alright. If it's less than or equal to... what happens if you try to realloc with the same size? Just absolutely nothing happens, probably, yeah. Which it'll handle with this, so... yeah, we'll just do else if new size is less than old size. We're trying to shrink the allocation, then what do we do? Well, we're just gonna need to like chop this block and then mark the second half of it as free. So we just overwrite this header. We still have old size, so we know how to get forward. Yeah, so we have this header write macro. We can write into here the new size, and it is allocated. Then, ooh, see, normally we step forward like this. What is it? Block P next, like next block pointer. Right, so since we just wrote a new header, this next block pointer will use the new header to get to what will be the next one. So, yeah. So we step forward and then write a new header. So, same thing, basically. It's going to be 3, and the size is new size minus old size. The only thing gotta make sure is, okay, size includes the size of the header, right? So one thing we do in malloc is we automatically include the header size. We need to do that here too. Whoops. What the fuck is going on? I think I changed this to, yeah, to take the size. So you make sure we have room for the header, because, you know, the user of malloc or realloc, they just ask for, say, 16 bytes. We need to include an extra one for the header. We initialize with that if we need to. But the point being, yeah, this is new size. Jesus Christ. Alright. Yeah, so if both of them include the header, then this works. Okay. Okay, otherwise, then new size is equal to old size, nothing happens. You know, we just return the same pointer. So that's fine. Are we getting anything else? Probably. I don't know. Let's test and see what happens. So the only way I can really test right now is I have this little shell that's, yeah, all this stuff's supposed to be, oh Jesus. Alright, so let's just, well, let's allocate, like, I don't know, 16 bytes. No, that's not what we want. It's not like, how do we want to do it? Like, allocate like this, or let's do it like this. Give me 16 bytes. Put it here. This is a pointer. And then we'll set it to, what? I don't know. 69, 69, sure. And then we're gonna reallocate, so, you know what? Actually, I wanted 32 bits. Realloc at N1, 32. So it should, we'll just print it as hex, I guess. And 2. Also, hold on, let's print, like, the pointer as well. And 2. And then up here, see where it's at as well. Alright, allocate 16 bytes, print it out, reallocate at 32. Wait, this is, I'm being so dumb. This is, yeah, this is in size bytes, so the fact that this is a U16 is meaningless, but this is what we did. We're fucking dumb. We can just take another one though. Okay. Sure. We'll see what we do. Oh shit. Wait. Oh, enjoyed the latest YouTube bot. Thanks, dude. Thank you. That didn't show up on. I don't know. I don't know how to fucking Twitch at all, but this didn't show up over here, so I didn't see that. Sorry, man. Thanks for watching, though. I think you're the only person that watches these videos, so great. Run. Is that where I'm at? Run. So we got issues. Yep, because I'm retarded. I am retarded. Where are we at? User age. Oh, so we don't have, also, is this completely blocked? No, you can see it. So we need, where's that? User age. You don't know about realloc, which takes, what, a void pointer probably? Pointer and size. Thankfully, you're not forced to use Windows for dev. Yeah, I mean, I used Linux for a long time. I switched over to Windows, honestly, for a debugger, which is hilarious because since I'm working on this little operating system, I have no fucking debugger. I only have printf debugging, but yeah. There's pros and cons to both. Like, I mean, I fucked around, trying to use GDB, but yeah. Alright, realloc pointer size. We also are gonna need calloc after that, but we can do that in a minute. Alright, does that work? Also, it's weird running this, since this is like a little toy operating system, it's emulated in QEMU, which means like the build is like a little more involved than just like compile. So normally I just have like a hotkey. I can just hit like F7 and it'll build, and then like in Vim I can jump to all the errors and shit, but I don't have that here, which is a little bit annoying, which is I have to do this weird jumping back and forth. Alright, so 181. So here it's new size. Same thing to here. Wait, what was that? It's on 184. New size. Alright, what the heck is this? I don't know what this is. How do I delete this? Go away. Go away, dude. What is this nonsense? I don't even know how to mod my own chat. Alright, what's there? Is there like ban and stuff? Ban? This one? Alright, we banned him. Cool. Alright, okay, well something happened. Alright, yeah, we're still doing like a little dump of the heap, which, I don't know, this is kind of cool because it shows you, how it grows and stuff. So first we called, malloc with 32 bytes. It's here at this address. Then we reallocate, so we asked for a bigger size, so it should have split it, which it did, right? So now you have these two. Actually, though, I think we didn't, so when we allocate and we move over, we're not marking the block that we just moved away from as now, like, not allocated. So we gotta do that. So we need to, where's the old one? The old one is PTR. So we copied over. Now we just need to header right at the old pointer. Old size is now free, non-allocated. Cool, so now we should see I'm a little confused. Shouldn't this be 0 now, right? This was the old space, so we allocated 32 bytes, which this must be in hex, isn't it? On where's the heap dump? Heap dump or dump heap? Wait. Oh, no. It's just, it's 20 because you include the header, right? Which, why is this 40 then? Shouldn't it be 32 plus 4? So it should be 36. I think I know what's happening. Yeah. We're increasing the size twice. Yeah, I told you I was gonna fuck this up. So we're just calling directly, in realloc we're calling directly to malloc with this new size, which already aligns up to a header size, and then you go into malloc and you align it up again to header size. Or not really, you align it up to 4 bytes, but then add a header size. So, how do we want to do that? Because it's nice having it before, like, when you have it here, it's before you even initialize, and that's nice. Because then, well, it's only, you probably don't actually need it in a init, because, like, init's gonna go by page size anyway. But let's say you asked for a large thing, and you need, like, and once you need the header, that's like 4 more bytes, it goes over to a new page. You're actually going to need 2, so the init is only going to ask for like a page less than you need. And then you're going to go into malloc and not find a thing and then have to go back to the kernel. So it is good to do that before init. Just trying to think of the best way to do this, because I could just save it here, give it to this, but then instead of mallocing, I guess we don't overwrite. You know, because I don't really want to say new size minus header size. Although we could just do that. I suppose that's fine. It's a little gross, but words do we use it in this function? Yeah, that's the only like outlier, so just do it like that. But I don't think that is yeah, this is actually wrong too. So when you memcopy, old size includes the header, and you don't want to write the header to the new place. So this is also minus header size. Yeah, okay. And then, you know, in the old one, you want to write out a 0, but why didn't that work? So you allocated 20 bytes. You have this chunk free. You reallocated. This still thinks it's allocated. Why is that? I feel like it might have something to do. Does it have to do with this calling through malloc? Yeah, I don't really see why that would be happening. So let's see. Once we get here, we're gonna say, at this pointer, I want to reallocate 2 bytes. Okay. Well, we line it up. That's fine. That's our old size. It's definitely bigger, so we're gonna go into malloc. Oh shit. An interesting thing is it's not just header size. It also aligns it up. Which in this case doesn't matter because header size is 4 bytes anyway, but we have to be careful of that. Which makes me think maybe we don't do this like auto inclusion of that so we don't run into this problem. So let's just do this so it's clear, right? New block size is this. Then when you malloc init, it's new block size. And then this is gonna be old underscore with old block. So old block size is that. If new can't type today. New block size is greater than old block size. Well, just malloc new size. And then yeah, that's still right. Old block size minus header size. That's how much we copy over. Then we header write into there. The old block size is 0. Okay. If new block size is less than old block size, write the new block size as allocated. Wait. Yeah, that's right. That's new block size. Step forward and write that is 0. Okay. It's like this isn't working though. Why would that be the case? One thing we should probably do is... Well, I don't know. I'm wondering if we should like assert in Realec that pointer is like 4-byte aligned. Because that's like one of the only ways we can know if it's a valid thing to try to free, you know? But I guess it's up to the user to not pass a bogus thing in there. Let's see what's going on. So, this block is still allocated. It's weird. We did fix the size thing though, right? So now this is 36. Which makes sense, but why are you still allocated? I don't get it. You're, header right. Get the header pointer. You pack a size and unallocated. Right? This clears the low bit, then this writes the low bit in. Why are you not... Pointer size allocated. I don't know. I mean, I wish I could just step through this in a debugger. I don't know. So we can say before, what's the header? It's going to be this size and whether or not it's allocated. This is block get size and then block get allocated. And then after. Should we, I mean, let's put the pointer in there, I guess, too. Alright, what is going on? So before, it's allocated. After, it's not allocated. Oh my god, I'm so stupid. I think it's been working the whole time. It's just like... The realloc happens after that? Is that what this is saying? Yeah. So, where does dump heap happen? It's in the malloc, so... We're just dumb. It's been working. But that did help us catch that the size was off, so thank you for that. So the value did get copied over, but it moved. So, you know, that seems to have worked with our terrible single test case. So let's check at least that shrinking keeps it in place, and let's do something like this. So let's say we put 16 bytes and then say, you know what? I only needed 2 of those bytes to actually put this in there. So let's reallocate it, and then let's do this. Let's say, you know what? I want to put another 2 bytes in, you know, except for now, of course, what are we gonna put in there? Oh, 420, of course. In 3, should've just done a replace, but whatever. So, I want to also kind of check if after reallocating and it shrinks, if the net following block is free. So this should get allocated right after this, and let's see if that works. Oh, we're in an infinite loop. We fucked something up. We fucked something up. What are we in? Are we in dump? We gotta be in heap dump. Or sorry, dump heap. Alright, what's wrong? Let me think, let me think. What's it look like? So this is trying to walk through the heap a bunch, and first of all, this looks like some kind of overflow. Oh, that's not right. So after one traversal, we're getting a full-on, like, integer overflow. Or underflow or something. And it's at this location? So did we've definitely fucked something up good. Real good. So, what did we get through before we hit that? Well, that definitely didn't... Well, we didn't put anything in there, but that's okay. But it didn't work anyway. So this is the next malloc. The next malloc tries to... find a slot. Well, that's weird because the heap dump happens after placing a new block, so... Let's do this. What does dump heap do again? Block pointer. Well, it's less than or equal to heap n. Okay, so probably what's happening is we're getting... Oh no. So the heap plus however many pages we have allocated as a UA pointer. Ooh, and another interesting thing is, well, no. God, I just wish I could step through a debugger. Alright, well, let's see. We want 2 bytes. I guess, do we just have to do printf debugging here? Wait, yeah, the interesting thing is, so this doesn't print, does it? No, so we're supposedly finding a fit and then placing a block, and then we failed. So maybe something's going on here that's messed up. Right? We can confirm that, right? By what just happened? We dumped the heap beforehand and we don't loop. We do still, so something's fucked before we place the block. And it's probably after the realloc. My guess is that's the problem. So we break it here. Which one is it? Which one of you fucked us? So it's the shrinking one? So what happens when we shrink? So we have a block that's currently 16 bytes. We're trying to shrink it to 2 bytes. So we write a new header that's 2 bytes. Well, you know, 2 plus a header aligned up to 4 bytes. Then, we've written that in there. We step forward by that new size. We write in there the remainder of the size that's left. Yep, we're stupid. It's the old block size minus the new block size. That was the overflow we were seeing. This size, it's because we're subtracting a smaller, you know, from the bigger, or rather the bigger from the smaller number, and it's overflow. So should have seen that. I'm rusty. Alright, now we got 420 that's here. And this is our new heap. We got the prologue. We got a 8-byte region that's allocated. We got a second 8-byte region that's allocated. And that's it. Because 8 bytes is what you need to store a header in 2 bytes and align it up to 4-byte boundary. Makes sense. Then this is the old section. You know, we used to have 16 bytes. We split it. This is what's left. Okay, then we have the original free block, the epilogue. Okay, we might have a realloc now. What a rough start. This should have gone so much smoother, I feel like. Alright. So now we can you know, if realloc actually works, which we should really test it much more. I should write some tests for it, like some kind of little mini stress test. Uh, you know, or we could just start trying to actually write some dynamic arrays, which seems way more fun, so maybe we'll do that. Do we need a calloc for this? I don't think so, so realloc might be enough. Let's start looking at what we wanted to actually do. So I stubbed a bunch of this stuff out, I think a long time ago. I don't remember when well, actually, some of this I did somewhat recently. Okay. So here's what we got going on, right? This is going to be the actual shell. What does a shell do, right? You give it a command line, it needs to parse that into arguments, and either you have like a built-in shell command that needs to run, or you're trying to run an external program with those arguments. So what I want to do is take that command line, parse it into some structured data, one might call a data structure, and then pass that to, you know, some evaluation function. So the way I have it stubbed out is like this. This isn't going to happen. So the other thing I want to do, what order do I present this information in? So I want to have a dynamic array of arguments, right? Which is going to look like this. So this is your command. You have a program name and then a set of arguments. Typically I use like Sean Barrett style stretchy buffer. Excuse me. But because I'm kind of starting with very minimal things, I'm thinking I wanted to try just a super simple like coding version of dynamic arrays here, where you just have like macros that expect a item length and capacity, and then just, you know, if length exceeds capacity, you reallocate, and that's it. Then you just bump length every time and put a new item in when you append. I mean, the thing I like about the Sean Barrett style strategy buffer is you can use the pointer as an array, or it's kind of the reverse. Like you can use the dynamic array, the stretchy buffer, as a regular pointer, and like all the metadata stored like before it. The same, basically the same thing that happens in the heap with malloc. Like we're storing block size and stuff before the payload. That's what the stretchy buffer does. But it's just a little more moving pieces. This is like literally a single macro, so I'm gonna use that for now. You're gonna have, all right, someone else in here. What's up? How are you doing? I'm good. What's your compiler for? Well, this is just a little operating system, not a compiler. Building a coding language? No. I have written a little compiler before, and you should check out Bitwise on YouTube. Per Vonson makes programming language. That's the language I implemented, his language. You can follow through that. But this is just a little tiny operating system. That compiler is actually where I learned about like parsing and stuff. So some of these techniques are used in there, which actually the next thing I was going to say is from that. What I actually want to do after this is, so this is one thing that I needed dynamic mirroring allocation for. CFilms, you just missed, we just implemented realloc, so that's what will allow us to, you know, have these dynamic arrays that grow when you need more size in the array. But so dynamic arrays need a malloc implementation, and then I wanted to have string interning. So C kind of sucks. Their strings are null terminated, you know, which can be a pain in the ass. And if you want to compare them, you basically have to walk through the whole string. What's really nice is if you do string interning, you can just do pointer comparisons. Like you can do a straight, you know, equals equals. It's quick and it's convenient. So we're gonna do that, but to start with, we'll just use the slow string comparison. So, right, you have a command. It's a program and a list of arguments. First step is to parse a command line into these structures. Why am I building this in C? Because I like C. That's what I program in. Simple language, and I like simple. I mean, there's some longer version of that explanation, but I'm a C programmer. I like C. I like very simple thing. You can like, you know, reasonably keep the whole language in your head, basically, you know. Anyway, let's start. So we have command line. We need to parse it into this command. So this is going to be due when we have string interning. We're going to have to like intern all the strings. So the way I'm going to do built-ins right now is a little bit wonky, but just store in like a static array the name and like a function pointer to how it evaluates. And each function pointer has this function prototype. You just pass it a command and it returns a pointer, right? Or it returns nothing, actually. And let's start parsing. So what makes C simple? Well, I mean, the amount of stuff in it. Like there's not much moving parts. I mean, you know, it was written in like, what was it, the 70s? It's like it kind of had to be simple. And like, I mean, think of it in comparison to any other language, right? Like, most people would point to like C++. That's a fucking nightmare. Like, I don't know if there's any human who knows all of the dark corners of C++, like all of it. Like, there's just so much shit in there. It's like you can hardly know what the fuck's going. Like, and look at the code bases, right? Like, if you go look at any C++ code base, it's like a different language. Like, it's an entire new universe of conventions and like how they write it. And like, there's a little bit of that in C. Like, everyone has their own style, but it's like it's understandable. The other thing is like if you try to compile a program in C++, the compiler spits out like this unintelligible muck of like compiler errors, and it's just a pain in the ass trying to like figure out what the fuck is going on. And I just find that with C, I never had that problem. It's just simple. And I mean, it's like has its foot guns for sure, but like, and it's not like a perfect language, definitely, but that's what I like. Yeah. Developing a new statistics-focused coding language. Oh, nice, nice. What do you do? Are you in school or are you working? What do you do? You just doing that for fun? Alright, what was it doing? Alright, we're gonna parse this. Command line, alright. So the first thing we're gonna do, clear the command line, because we're in a loop, right? So we're just gonna keep reusing this buffer to read into, and this is the command that we're gonna pass on. So yeah, we're just parsing and then evaluating. So to parse, what do? We don't have that yet. There we go. Alright, so the first thing we're gonna do, right, so this is gonna be easier too. Once we have string interning, we can read into like, some separate arena with all of the strings, right? And we can do straight comparisons, and that memory will be stored in like, its own arena. Right now what we're doing is we're using the command line buffer as like the owner of it, because it's gonna die after this anyway, so it doesn't matter. But so you have the command line as this buffer with whatever the user typed in, and we're just gonna like step along until we find a space and just like poop down a null byte in there, and then that's gonna be like the string, and we're gonna point to the beginning of that, and that's your null terminated string, right? And so, in here you just step through the buffer. If you ever see white space, so like a space, a tab, vertical tab, I don't even remember what that is, but it's another sort of white space. And then, you know, every time you do that, every time you find a space, you poop down a null byte, and then, you know, that's how you know you're starting a new argument. If you're starting a new argument, well, add it to the argument list. Right, this is the pointer to the beginning of the string, and it's, you say, all right, it's no longer the start, and then you're just gonna keep stepping forward. And once you hit, you know, another space, you'll null terminate that one. Then you gotta be a little careful here at the end, because you gotta null terminate at the end, which we can do because a command line ends in a new line. Sometimes your data analyst, nice, okay. Sometimes it gets as bad as 40k error messages. Yeah. Yeah. Is C very imperative? What exactly do you mean by that? Just like, you just say what you're gonna do rather than how to do it. Like in that sense, yeah. I mean, it's not like, I'm not really familiar with like functional, you know, hardcore functional programming type of style, so like where you do like case matching and on everything. Alright, what was I doing? Yeah, okay, so this DA append will now work. This is what we were, you know, went on that whole tangent the other day about writing an entire dynamic memory allocator so that we could have this append. So let's make sure this macro makes sense. So you pass it a thing that has a items member, a length, and a capacity. Well, alright, I just talked about how awesome C is. This is the thing that kind of sucks, is like, you have to use macros sometimes to accomplish what you want, which is not the best way to do things, but you know what? It's better than templates, so yeah. Oh yeah, definitely not OOP. I mean, you can do OOP-ish things, but it's like not the default way to write programs, which is another thing I really like about C, is like, if you are writing in C++, it's like, you know, the world at large basically assumes and expects you to write in OOP sort of fashion, and like, I'm not a fan of OOP, so I don't like that. And in C, I mean, the default way you write C, like if you go read any C code base, at least the ones I've like gone through, they're just like, all right, what's the code I need to solve the problem? And that's the code they write. And it's so much easier to read through. You're not searching through like 12 different classes to find like where the fuck is the actual functionality. It's just like, here's the code that does the thing, you know? And it's not like if it's a straightforward set of like 50 lines that does the thing, if it's 100 lines, if it's 1,000 lines, like you just write that and that's in there. It's not like, oh, we can't have this function be longer than 10 lines. We got to break that up into, it's just simple. I mean, so like the language is simple, and I think it also lends itself to writing simpler code. Yeah, I think it's much better all around. But as I've proven, you know, in this stream already, I'm an idiot. I've been fucking shit up a bunch, so don't listen to me. Okay, so if the length exceeds the capacity, we're doing a dynamic array append. If the length exceeds capacity, we need to reallocate. So how are we doing that? Do you already have a capacity? Because this could be an uninitialized struct like this, right? So if it's uninitialized, we're just going to start with 32 as initial capacity, which I think is reasonable. I feel like most, or often, you're going to have small. We can tweak that if we need to, but the default size is 32, and then you just double each time. Makes sense. Yeah, and then you do the reallocation, capacity times that many items, yes. Then you bump the array length. Yep, 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 yep. Okay. An interesting thing about that is that you don't have pointer stability in these types of arrays, but it's fine because we're storing pointers to strings that live elsewhere, so it's all good. Alright, so this looks good. We can append an argument. String returning we're going to do later, so then you just return the command. So parsing should, in theory, work now. So we should be able to get rid of this bullshit. This is now main. We're going to parse. We don't have evaluate yet, do we? What does this do? Yeah, so this was like the very, very, very first little tiny shell that I, threw together to have anything at all. So this stuff can go. We can maybe look at evaluate in a second. What I want to do is make sure parsing works. So honestly, we don't even have to call it. So the name of the command and then what is it? Commands args length. We just print this argument. So each one you want a space argument. We could even do like comma space argument, I guess. Okay. Args items I. That's the other thing that's, a little annoying about the Soding style dynamic array is like you have to store it in this external struct, so you end up with this items after, because what you really want is just like items or args at I, but you have to do args items, which I like the stretchy buff version, but I'll bring that in here at some point. It's just a little more moving pieces. Honestly, it's just like you need the grow function and a little bit more macro like magic. Coding language I'm developing is simple and not OOP. Nice. So what is it? You writing a compiler for it then? Or is it like an interpreter? Let's see what this does. Alright, we got errors. So we can just do U32, I don't care. I don't really care about those. Built-ins. Wait. Why is this an array of pointers? It's not. These are just the thing themselves, right? Yeah. Ooh, this is pretty sick. Alright, forgive me for this. that was tight. And we got a nice little fucking kernel panic when we tried to run that, so we fucked something up. Dig, lots of your Spotify posts. Sick, thanks, dude. Yeah, I love music. I got like ridiculous amount of playlists. Alright, so what's going on? So I tried to, what do we got? Here. Let me. So let's see. We tried to parse. Where were we at in line 900 and kernel? So we're in back vAdder with physical address. So in trying to allocate some memory for the shell, this insertion failed. So right now we're assuming that you're trying to access memory in your heap. So what we should probably do is print out the address we're trying to access and maybe so this would be useful next time. I don't have a good way to do this, do I? Assert the condition and a message. Okay, I guess we can have an additional message. I'd really like it to be optional. Can't really do that with that anyway. Alright, so message. Assertion failed this condition because of this message. Okay. So, where were we? Here. Fuck. We actually want to have like a format string, so you want to be like some format string here and then the arguments. So we're gonna have to do something like this. Format and then the arguments. And then it failed because of oh wait, we're passing this to Panic, which already can handle that, so this is actually kind of perfect, right? Because can't we just say, well, we still have to pass that to this macro, so yeah, we can just have this handle it though. We can say this failed. We don't need the format, we just need the args that follow it. And then we can say this failed because of this reason. And the reason is what are we passing here? Like VA args? We just pass the arguments on, so this is the rest of the arguments, I think. So like the literal args like that. That's var args, I need VA args. So pass on the condition and then feel like I'm a little off with something. Because if you do kernel cert without a message, what's gonna happen? You're gonna have another thing here. It's gonna pass it. It's gonna pass nothing on, but expect it in here. And then this is gonna put file line. Then your format string in there, and these are the args. Yeah, so this is your format string. So maybe what you really want is just indicin mess. Wow, that'll break. How many of these do we have? I'm just gonna be lazy. Okay, we'll just do it. Do a message, and then message. Alright, search and failed. This because of this. Sure, and then everywhere we do this, this one. You know what? I'm not saying anything else right now. For you though. Oh wait. Ah, I'm so dumb. The whole reason I was doing that is because we also want to pass a format string in here. So yeah. It's like a little bit convoluted. Like what I want to do is say, like, I don't have a sprintf either. I could print to a temporary buffer right here, but what I want to do is say heap start is here, heap end is here, v adder is I guess the same. Current proc, heap start, current proc, heap end, v-adder. So like, this is what we want. In order to facilitate that, kernel assert needs to take this, then like a format and these arguments, and then build it like this. So like, we can just depend onto it the same way. So like, assertion failed this because of this, which is a format. String, sure. And then you have this. So you have, we can't, yeah, we call it that, right? So format is used here, condition is used after that, in the first one, and then we spread out, the args here, and this one. Maybe that's what I want. Do this work now? Okay, so the starts here, the ends here. We're trying to touch this. Interesting. So I think this is like not actually. Yeah, I think I know what's going on. Well, kind of. I think there's perhaps other reasons why, because right now what I'm doing in handle trap, right? So the way this works is when malloc needs to get more memory, like on initialization, for example, or when it runs out of memory, it asks the kernel for some more pages. It does that through system call. The system call gives a set of virtual addresses back to the process that, malloc was in. Then, whenever the process attempts to access either through a load or a store that virtual address that was given back from the kernel, well, there's a page fault. The CPU tries to read that, and it does that because it's a virtual address. There's page table entries which have like flags in them, and the one we're checking is there's just a bit, there's a valid bit, and if the bit is invalid, we're assuming that that means that, oh, this process is trying to access a page that is in their virtual address space that they have been given to the given by the kernel, but have never accessed before. But I don't know that that's for sure the only reason why the valid bit would not be set. And I need to verify that assumption somehow. So right here's the trap handler. So this is what would get, so when the CPU hits like a read, a load, or a store, did it tell us what kind of fault we had? Nah, because we end at this assertion from two different places. It could either be a load or a store, but it's probably a store because we're writing into that memory. But so when the CPU tries to read one of those addresses that's not mapped yet from a virtual address to a physical address in memory, it has a page fault exception, which the kernel can handle. So it goes to this trap handler, right? And then there's a control status register that the CPU puts some information in. So we're reading some values out of that control status register. The cause, which is basically like an enum val that can have like the type of trap it is. The stval is like in our case it's the address, but it's like the data basically. It's the value that you need. The UWC is the program counter that the like the application code, user space code was at when it encountered this exception. So we hit either a store page fault or a load page fault. First thing we do is check if this is a first access. We're doing that by checking the page table valid bit. So if the page table entry, that's what PTE is. So if the page table entry has a 0 bit for the valid bit, we're saying, all right, this must be a first access. Then we try to back that virtual address with a physical page in memory. So we try to map that page. I have a helper assert here that's saying, hey, is this address actually in the heap of this current process? If not, something's wrong. And we're getting an address that very much looks like a specific type of failure. Like there must be a reason for this. Like I feel like that even looks like a like a jump vector where you would put like where you would register a handler or something like that. The thing is I guess what we could do, I mean, this would let us move forward, but not actually really totally solve the problem, is we could say, hey, when we are checking if this is a first access, do this check there and say like, hey, is this in the virtual address space of the... Well, we're going to have the same problem, because for some reason we're hitting this page fault. And our value is FFFFC. So it's 1, 2, 3, 4. Just trying to see if this is like a known offset. My knowledge is like really fuzzy here, because this is the first time I've ever done anything like this, and I don't know what else would cause a page fault. It's got to be these reads, right? Because like if I didn't handle this, it's gonna hit this anyway, like an unexpected trap. So I'm thinking maybe we're trying to access like a wrong... Maybe that is actually the address we're trying to access, and it's not like something else going on. So let's verify that. So what are we doing here? We could just do... We could make testing a little simpler by just doing this. Actually, we don't even have to do that. We make a new main and just try to test this dynamic array thing. So what's the one we have? We have arguments. So let's try to make one of these arguments and say wait a minute. What happens with realloc if you pass in a null pointer? Because that's what we just did. That's probably our problem. Yeah, because I don't think we handled that case. If you realloc and you don't have a pointer, that's basically malloc. Right? How does, like, the C standards tell us do that. Let me just look this up. Does it tell you? Realloc. If pointer is not null, it must be previously allocated. If pointer is null, the behavior's the same as calling malloc. Yeah. This is definitely our problem, I feel like. So, realloc. Yeah, so if we don't have a pointer, we just pass this on to malloc. New size. One, two, three. Actually, we didn't. Wait, what? I'm confused. Why did this even get called? Did we not recompile? Did we not save? Maybe we didn't save. That's probably why. Alright, let's see. So we saved this, but not this, probably. Alright, let's fix these warnings. Let's do 32-bit comparisons. It's fine. I mean, these are getting cast up. The reason it warns you about those comparisons is because it can be real dangerous when you have int and uint comparisons, because in C it's going to auto cast up any integer to its, like, in this case, when it's like a signed 32 and unsigned 32-bit integer, and you're using them in like binary operation between them, like this comparison, it's gonna cast the signed integer up to unsigned, and you know, if that's negative, then you have a crazy big ass number, and it can be like, you know, bad shit can ensue. In this case, it wouldn't have done anything, but the warnings are good. Anyway, the warnings are good. So let's see what this does. Okay, so this should be fine. It's trying to... The virtual address that you're trying to touch is the last byte in the heap, which I guess is true. You shouldn't have access to that yet. Like, you shouldn't be mapping, like, this assertion's getting hit when you're trying to map a virtual address to a physical address. And this points to, like, the end of the heap, so there's nothing, you don't actually have access to this virtual memory yet. So why is this getting hit all of a sudden? Why are you trying to access this anyway? Like, you have a page basically free right here. This is the end of the heap. Why are you trying to access that? So we probably have another fuck up somewhere. So you're assigning this to... Yep, so I think we do need to do this actually. Simplify this for testing. Args is this. We're going to append to args A new arg. So we can just use the static. I might have to wrap this. I don't know how well this is gonna work. Oh wait, we do. We have items. Oh yeah, it is this. Char star pointers. So I don't know. Um. Whatever, some bullshit like this, then you can do names 0, but you need to append by pointer. So you want the address of this. Why? Why don't we just do this like... Nope, that's right. That's right. It's this. Name 012. I guess we can just see if this crashes. Ugh, gross. It's not a pointer. Yeah, okay. We have to append to this. So here we didn't explode. So that's good. Let's do unsigned comparisons. Why it's less than args when print the one, two, three. So dynamic array seems to be working all right. Let's do something like this. Let's just nonce. Let's put like I don't fucking know, like 10,000 of these in there. And see if we explode. So, yeah. We're just gonna put a bunch of ints in there, and then... just, Argsland. Just print the length, I guess. Just see if this explodes. No member named items. Ah, shit. That's the other reason I don't like this macro thing. It's like they have to be items. Nums. We got rid of that. Okay. Item. From Entichar star. Wait, what was that? DA append. What is this on line 80? Right, because we changed this. This thing doesn't exist. Oh, God damn it. Numbers has ent items. Okay. Numbers. Numbers. Okay, we have fucking numbers. Alright, we did 10,000 allocations. We got 10,000 numbers. This is our new heap. That's not the problem. Our dynamic array is not the problem. So we just have probably a business logic error that we fucked up. It's funny the growth pattern, right? Like, because we don't do any coalescing, like, you just double each time and you're like, you know, this size is too small, we double it. This size is too small, and we're just making these big ol' like empty blocks. Yep. Once we do coalescing, it'll combine all of these into a single free block, so then you won't have all this like fragmented little spaces. But that's pretty cool. So that part's working. So let's see what's going on. We probably just did a little fuck up somewhere. So let's maybe simplify this a bit, right? You clear a command line, clear a command. You're just setting up the actual command line. When you parse it, what's going on? Well, you make a new command on the stack. You set the program, so you point into the line, right? You set the pointer to the start of the line. Then alright. I don't really see it yet. Command line is that buffer. That's a pointer. It's a weird thing about like pointer decay, right? Because you want to think about this like an array, but it decays into a pointer. What you would really do is be like, hey, take a pointer to this, which I think it supports anyway, but like it's just gonna, you can do this a million times if you want, but you parse the command line. Yep. If it's the start of a new argument, well, you want to put that pointer into args. Args, so it's an array of string pointers. Or like car pointers, which are strings. An array of strings. You just have pointers to them. That makes sense to me. What was the symptom again? Yeah, like you're trying to allocate at the end of the heap. Why is that happening? That's a weird thing that's going on. And why didn't it happen before? DA append. So if length is greater than or equal to capacity, well, right now I think this is the first allocation, so length and capacity are both 0. Because we did 0 initialize it, right? Because this command's on the stack, isn't it? Parse, command 0, so we did 0 initialize. Length and capacity are 0. Wait, this isn't the argument, this is the arguments. Well, we mem set it to 0. Oh wait, no, it is a command. Right, in parse it's creating a new one too. Yeah, it's clearing it, which contains the arguments, which also sets the arguments to 0. So all of these are 0. The length is equal to capacity because it's 0, so if there's a capacity, there's not, so it's 32. The items, we're going to reallocate items. Okay. So this is 0, so you have a null pointer. Capacity, which is now 32, times the size of a pointer. And we're on RISC, so that's RISC 32, RISC-V 32, so 4 bytes. 32 times 4 bytes. Okay. What was that, 128? That's what we should be expecting into realloc. Since it's a null pointer, realloc just calls out to malloc. Malloc needs to initialize probably, which is fine. Then we find a fit for 128. Which is what this should be, right? Because 128 plus 4 bytes for a header, that's 132. So this allocation seemed to have worked. We found a place for it, we placed it, then we dumped the heap. So this is where the command lives in memory right now. We return a pointer to that. Now items points to that. We bump the link. and then put that pointer in there. What's weird, yeah, we dumped the heap, so we're returning. So it's in the access that it happens, so it must be here. Do we need to, like, do this? That would be annoying. This is postfix increment, so length is 0. You should be accessing the first byte of this and putting that pointer in there. But it seems you are not. This song is kind of sick too. Alright, that's a problem. We're appending too many times. Why are we doing that? We should include the new line in there, so that should be there. So, command line. We're parsing that. Cool. So we're stepping. The program name should be first, which we said there. It's not 0. So we're not going to append this arg, which makes sense because, you know, the first one's a program name, not an argument. So we should be just stepping through this, stepping through, stepping through. The thing is, we can't really print the arg here because it hasn't been null terminated yet, so we can just print the command line, but that's always going to print the program because it's null terminated there. So, I mean, what would happen if we just put, if we just try to spit out the current argument, right? It's gonna like run to the end of the line, but then keep going until it hits a null byte, so perhaps this is gonna vomit characters onto my screen, but we'll see. Yeah. Parsing 1, 2, 3. The first time it says it's appending 2, 3, which makes sense, because, like, this is what we actually want. Okay, then we're appending 3, which makes sense. And then after that, what's going wrong? We're not... If we are encountering spaces... or tabs, or V's, are we, do we hit like a carriage return? That we don't handle? Because right now we're only saying like, hey, look for the new line. Carriage return. I guess you could say either of those. I don't think that's what it is, but maybe. It's not what it is. Okay. So we just keep going. We're hitting other kind of characters. Maybe? Or is it not actually... Parsing 1, 2, 3. Is it null terminated? Are we null terminated? The parse. Oh yeah, so we did set this to 0, so I don't think we're handling the null byte. I'm just saying, what's the best way to write this? We could just say like, do we write them out here? Like, if it's either of these 3 break, do we put it in the for loop condition? I think this is what's happening. Nope, still not. Bro is John Blow. Nope, I just stole his color theme. Yep. This is the John Blow color theme though. The colors are so good. Come on. You can't deny it. Alright, so why are we accessing the last bit in the heap? Right, we're still appending, that's what we're doing. Yeah. Why are we hitting that? This is some stupid ass simple parsing. I guess, I mean, I want to understand what's going on, but we could also just say like, hey, if this character's not in the printable range, just like fuck off, which is what we're getting, right? Because we're getting somehow. Well, the first one is like space, so maybe there's other space characters that we're not accounting for, which I thought verified, right? We have is space. Form feed, line feed, carriage return, horizontal tab, vertical tab. Form feed, I think is what /f was. Line feed, carriage return. Wait, what is line feed? We have tab, vertical tab, form feed. I mean, did I implement an ispace? We could check that. Yes, we did make ispace. Yeah. Okay. So since we're already ruling out suppose we could just do, let's do this. If is space that, just poop down another 0. Try that. Somehow it's worse? What the fuck is that about? So oh, right. So what's happening is like we're having spaces and then things that we don't handle. When we get the space for setting a start arc to true, when we get in here, we're hitting a character that's not like. Do we have an assert? Did I implement an assert? I did, so. I mean, I want to see what the thing is, so let's just do this. What's the printable range? Do we have his print? Is printable? We didn't do that. We should do that, but alright. If let's see, is less than like that, or C is greater than that. What's the fucking bytes that we're getting in here? Oops, we got this. It's this. I mean, I guess we just want to crash hard still. There's zeros. But if C0, you're supposed to break out of the loop, right? Am I retarded? I am, in fact, retarded. Okay. Yep. Yep. That's your favorite phrase in all debugging? It's like true 99% of the time. It's like, oh, I'm just a complete idiot. Yep. Yep. Alright. Alright. Okay. We now have Arguments, cool. So, I feel like there's another weird thing that was going on though, because we were hitting that kernel assert that was like panicking. Why? Lots of oopses. Too many oopses to get through. That was before. Oh, right. It was just because, yeah, we were trying to like append 0 bytes. Okay, that's fine. That's fine. All right, so we got a command line. Let's evaluate this. So, we check if it's a built-in. How do we do that? We go through all the built-ins. We don't have string interning yet, so we're gonna have to do string comparisons. Compare program name if it's built-in true. Then we just dispatch to whichever evaluate function is in there. Then if it's not, we have to find the program it's trying to run. This is where it's going to be interesting. So the reason I moved to even trying to work on the shell at all is because before this, I had implemented a file system, a different one, VSFS, which stands for Very Simple File System. And it's like not we haven't implemented that fully on the kernel side. Um, so this will force us to do that. Like we needed a way to try to like move through directories and stuff. So the shell will get us a way to do that. Because right now all we're doing is when we boot up, the kernel initializes the file system by just like reading in the metadata basically, like a super block, and saying like, you know, is it valid? And this is where everything's going to live, but it doesn't access anything. So this is where, you know, well, actually not here. I guess it'll be in the built-ins where we try to like change directories and like read directories. So let's start doing some of that. So let's just give ourselves like a CD. So we need the concept of a working directory. Oh, I already did that. So we have a working directory which starts at the root, which I suppose makes sense. We stubbed these out. Great. Shit. Have I been typing like behind my face? Is that fine? I don't know. Hopefully not. Let's start with I guess parent working directory is easy. It doesn't even have arguments, right? So should we do this so the compiler doesn't freak out? And then we just print working directory. Alright. We don't have string interning yet. Uh-huh. Alright, well let's see how many things we already fucked up. Let's get rid of this warning. What's going on? Oh yeah, stupid. What? What is num built-ins? Unsigned? Yeah. We can make that an int, I guess. What's the working directory? It's definitely not that. Where was that? Wait, what is it? This is where that came from. We're not calling it. That would be good. Alright, working directory is slash. Great. Look at that. We have a fucking fully functional shell now. How is that? Right. We can print working directory. We can end the stream. Okay, let's do CD. Let's do dir. We need dir. We're using Windows dir instead of ls. Bite me. Ooh, this is sick. I missed the sick part. That's alright. Alright, so this is gonna be more interesting. So for dir, what do we need to do? We're gonna have to actually access the file system. So we need to read directory with path slash. So what does that look like? We have to we know where the root inode number is, so we start there, which in this case is root, is what we're looking for, but we start at the root inode and look at that entry in the inode table. I mean, we're not going to be doing that in the shell. It needs to be implemented like... This is what, you know, it's going to end up happening over on the kernel side. So, the shell's just going to be like, you know, like give me all the entries in this directory. So you need like a, what is it? Like on Windows you do, what is the thing? I don't know. There's like a reader is I think the, like POSIX thing, right? Is that right? What does Windows use? I don't know. It doesn't matter because this isn't Windows or Linux. We can do what we want. I guess we could do something like reader. Reader. Current, or what is it? Working directory. What does that give you back? Oh, right. There's a reason, I think Linux does the like one entry at a time sort of thing, right? How does reader work? What's a good interface for that? Reader directory. So it takes a dir pointer. So you have to get one of these. You have to like open open that path or something. I think that's how it works. Like you give, there's a function where you pass a path in, it gives you back this like directory stream, I guess, and then you reader to get entries out of it. And then how do you know it's over? So you just read until you get error now? Yeah. I mean, so that's the Linux way. Internal pointer variable. What's up? What's up, Zen? Yep, that makes sense. So how do we want to do it? Should we do the same thing where you have an interface that's like, you just keep reading directories? Read it with India voice? Are you from India? How do we want to do it? I mean, I don't want to think about like API right now. I want to get to the kernel side stuff and think about what we're going to be doing. What did I just do? Oh, whoops. Let's see. Well, we need to have a syscall for like opening. These are bullshit. These need to disappear immediately. Read file and write file need to go away, but we can do that later. So it's probably like you have like open calls, so you can open it. That's when we're gonna actually touch it on disk and actually bring it into kernel memory. And then have like read system calls. First. Yeah, so we did this when we were writing the file system out, we used Windows' thing, right? I want to look at that real quick. So if we go look at our utility for writing a disk image, we did, so the first thing we did was like read a directory structure, like traverse the whole directory structure, right? Which I think we called traverse dir, yeah. Traverse dir. So the first thing we do is read the host path with reader. Like this is basically what we want to implement, but on our operating system, right? So what did we use? You use find first. So it's basically the same as Linux, right? You say like, here's a path. I want to give the first thing, which is either going to be file info or directory info, and you get back a handle, and it fills out the struct, which has like what in it? A name and like a size probably, yeah. What are you trying to do now? So a bunch of things that got sort of wrapped up like that depended on each other. Like so first thing I was trying to do is implement like a new file system for this little toy operating system I'm building. So, you know, I'm using this file system called VSFS, very simple file system. And what I've done so far is like wrote a utility that given a directory on like your host system, you give it a path to a directory, it traverses it and writes that in this file system VSFS. And now to use that in my operating system, what I'm doing is like on boot up, the kernel like initializes the file system by checking magic numbers, reading the super block, seeing like basically reading the metadata about the file system and that's about it. So now what we need to do is like, all right, now we need to access the file system, but in order to do that, I need a shell that I can do stuff with, right? So I started working on I had like hardly a shell at all on there. Started trying to implement that. For that, it's quite useful to have dynamic memory, right? You want to have like dynamic arrays and stuff. I mean, you don't need that. I could have totally just like had a big static array, but like I'm trying to make the, use API that I actually want to use. And so I had to implement malloc. And I did that and realloc so I could have dynamic arrays. Now I'm back to the shell trying to implement like directory traversal commands like built-ins. And right now I'm doing like dir or like ls on Linux, like just list the current working directory, the contents of the current working directory. So to implement that command, we need like system calls uh, that lets you access files in the file system. So um, I'm just thinking through, how the hell do I fucking do that? So like on, it seems the way you do it on like Windows and Linux is you give a path and kind of keep calling like a read dir or find next file function that like steps through like given uh actually how does it work on, does Linux give you back the whole thing? Or no, it gives you back like inodes each time. But yeah, so we're gonna need to like step through a directory and like start reading it. And so like the structure on disk, like our file system has a thing like, I think in the data block you write out like the actual dir link things is what we call it in here. So I'm pretty sure this gets almost directly inserted into the data block, right? So you have like an inode number, entry size, a name size, and the name. And then the inode knows the type. And the inode num is just a index into the inode table. So is this definitely what's on disk? Where do we write these out? Traverse dir. Where do we write? Write entry. So if it's a directory, What do we call it? Why is the naming so hard? Naming sucks. We need a directory back. Dir handle. Directory. Or do we return like the directory entry? We'll just think about it, I guess, for now. We can. It's gonna change for sure, but all right. So if we I don't know, we can like do while loop it, I don't know. Read an entry. I guess we need. I don't really do whiles that often. Is this is not, yeah, there's a scope here, so I guess you'd have to do something like this. Probably a pointer. Or no? What's this stuff gonna have? We can just write it out, you can copy it. Or we just do the fucking C thing and have a return code and we just write it into here. Can do that too. It's like, what is it? Almost 2 a.m. I'm tired. I was up till like 4 last night. Because my dryer went out. The heating element went out and I had to rip my entire dryer apart. Get the fucking heating element out. How do we want to do this? I mean... Do we want to do codes? Or do we want to turn like return pointers that can be null? I guess you could even I guess the reason for returning a handle is so you can like get the next one, right? Otherwise, reader itself has to like keep track of where the last thing you know, the last time you asked for it, which isn't that bad, but I might have to do this tomorrow. I'm like dying. Let's try to go a little longer. Let's try to go a little longer. Okay. Let's lock in. Go to bed? Hey, that's my girlfriend. What's up? She wants me to go to bed. What's up, babe? Love you. I'm not gonna go to bed yet. I'm gonna keep fucking tell me what to do. I'm gonna program, do what I want. What the fuck was I even doing? Okay, here. We're gonna do codes, I think. Codes. Let's just start with codes. Oh shit, I was like accidentally moving this stuff around, wasn't I? Okay. You got me flustered. Alright, well, return code. We'll just do the for loop. We'll do the for loop thing. So, we need an entry. We pass that in. Okay, we're looping. No, we want the handle. Because we did reserve a zero, the zero index is reserved for like a non-use thing. So if we do handles, we could, a zero handle is like definitely not a valid inode. I don't know how I want to fucking do this. Let's think about reader. You know, which version do I like better? I'm thinking that like the Linux way is kind of nice because whoops, where's my shit? You know, if you return like a pointer to one of these, then like you know, when the kernel reads in like inodes, you can just hand back a pointer to that memory, right? So if we do it like that, then if that's null, we break. And we're just we're going back to literally the first thing I wrote. Right. This ends. And then we do the while. Why is this? Oh, space. Right. Okay, so while you have an entry and you're gonna assume the first one works, which might not. Well, in the current working directory it should always work, but you might pass in some bogus So I guess you can do the dumb thing where if you get one, you just print the name. Or I guess first version we can just print it immediately. Yeah, alright. We're gonna want to print more info. File size. I don't think we keep track of time and stuff right now, but like we can just print file, name, and size to start with. Entry, name, entry, size. Huh. I must be exhausted because it's taking me forever to write the dumbest fucking code ever. Like, it's such an easy thing to do. Well, entry. It's just a fucking copy of the whole goddamn thing again. Alright. You just keep fucking reading those things and printing out their infos. Alright, I'm glad that took me 20 fucking minutes to write a for loop. Great. Let's try to implement a reader. So, where do you want to put this? This is like user. We don't have modules split out like at all. We just have all of user space in a single file. So let's go check out that file. Alright, we can close this out for now. This is all dynamic memory stuff. We'll put it I don't know, above that. So reader. You're gonna give it a path. Should we call this? That's fine. Okay. So yeah. Do you give it a path? No, you don't. Because you need to give it like the handle. That's the whole point of all this. So you have maybe like I don't know, something like a dir handle is open dir. Should it be the other way? Should this be dir read or like dir open dir read? Naming an API stuff is so fucking annoying. It's just like a billion possibilities. Alright, we'll rename this shit later. Open path, which is, we'll start with working directory. Alright, so you read through the handle. Alright, this takes like a dir handle. What is this? Alright, we're just gonna fucking jam for a bit. So you're probably gonna like get back a file descriptor from open or something like that, and then you can like construct a dir handle with that in it. What all do we want in this handle? Should this be like completely opaque? Like, it could be a pointer to one of these things that you return back but don't expose or something, you know? Could be one of those deals. Should we return like a handle or a pointer? Probably like an opaque pointer to one of these things. The offset maybe, so that we know like the last place we read. I don't know how loud this is, sorry. What all do we need in this thing? So, if we had that, then the next call, you know, when you call readdir with the handle, you know the file descriptor. So like, the kernel's gonna have like an open file table that's indexed by file descriptor, and I guess isn't that gonna, well, like that's gonna have its own like pointer, like an offset into that file where it last read from. But like that can't be sure that like. Ooh, so many questions. Like, how does that work with maintaining like a offset for a file descriptor? Like, in the file table, is that where you handle that? Because like, couldn't or do you hold metadata per process? Probably because like multiple people could be. We just made a dynamic memory allocator, so we could just malloc it, and then when you close it, it frees it. You know, or we could have like a static storage for it. Um, how do we want to do that? I don't want to think about it right now, so let's do this. Alright, return the handle. I mean, check if path is a valid door somewhere. We gotta make sure this all works out. Make it a valid file descriptor. But assuming we do, we can do something like this and return the handle. And then, reader. What do we want to do in here? Well, we just want to get the next directory entry. Which is going to be something that lives, like, in the file table, I think, right? And then, so where do we store this? So like, entry. I mean, you could have some like static storage for that and like use the same entry every time. What's gonna be in a dir entry anyway, though? Like, for now, all we care about is like a name and a size. And we can fucking copy that shit out for now, so that's fine. This is gonna be wrong, but we'll fix it when we get to it. We can try to figure out what the right thing is. So get the next entry in the directory. 22 by handle. So maybe we're gonna do that. It's like the handle's gonna keep the offset in it so that somehow you can tell the kernel like, hey, look at this. Like you have this file open, which is like a directory file. At this offset, this is where you're at. So given its size, or is it? Yeah, you need the size Like you need the size of the name because that's how far you need to step forward and like that tells you how far you need to go on the disk because you have like a standard size data structure and then a variable size name. Which, yeah, okay. But I'm getting stupider and stupider as time goes on, so I'm gonna dip out and try again tomorrow because it isn't working so hot. Give my brain a rest. But cool things we did is we got Realloc working, fixed some shit in Malloc, so we have dynamic memory, so we can do shit like this now. That's tight. That's pretty tight. We still need to do coalescing of free blocks, because there's no coalescing right now, so blocks just, you know, little, they get unused a lot. But we can do that. That's gonna be interesting too, because to do coalescing, like, it's much easier if we keep a header and a footer. We just have a header right now, but if we duplicate it, we can look back, because like wherever you are, you want to see like, is the block in front of me free and is the block after me free? Because then you could combine the whole thing into one block. And in fact, you can just keep, while you have that, you can just keep expanding that out, you know, until you coalesce like the largest possible block. Otherwise, with just a header, you have to just traverse the whole thing. So yeah, we're gonna do that. I can figure out how I want to do how I want to handle like reading files and directories, how we're gonna store that, how we're gonna do like open file table on the kernel side. Uh, so many things to do. So many things to do. That will facilitate shell commands for navigation. Yeah. Yeah, we're doing stuff. We're doing stuff. But we're doing stuff tomorrow because I'm tired. Okay, bye.